Okay, I just want to do a follow-up to molecular orbital theory and provide some reactions where you can see how molecular orbital theory works. So if you use HBr and butadiene, if you add just one equivalent of HBr, you get two possible products out of this. Mechanism of this is you protonate to form the most stable carbocation you can. And this carbocation is the most stable one because it's resonance stabilized. And the bromide adds to either resonance structure and it gives you a mixture of the products. Where molecular orbital theory comes in is you can take a look at the molecular orbitals of this type of system and predict where the bromide adds. So this is what's referred to as an allylic carbocation, where the carbocation is on a carbon adjacent to an alkene. And each of these carbons right here are sp2 hybridized. That means we have a conjugated system of 3 p orbitals in a row. And to come up with the molecular orbital diagram for the pi system, we have 3 orbitals in. That means we have 3 orbitals out. 3 molecular orbitals. And they have 3 energy levels on this. And if we take a look at the allylic system, the lowest has 0 nodes, the next has 1 node, and the highest has 2 nodes. 0 nodes means they're all in the same phase. Two nodes is if we put them as symmetrically as it can, or the nodes are there and there. Now the problem is with the 1 node thing, symmetrically, that goes right in the middle right there. Okay. Now it's easy to see what you do when a node is between atoms. You just put the node in and then you switch the shading across that. But when a node actually falls on an atom, essentially what that means is that atom doesn't have any electron density possible at that point. So when you throw a node right on an atom itself, think of it as it just winks out. And so then you follow in like this. So this is the molecular orbitals of the allylic system of 3 p orbitals. And we have 2 pi electrons. Those 2 pi electrons, you fill it in each molecular orbital. So 2 electrons go in the bottommost one, and then we don't have any more electrons to fill the uppers. This is what's referred to as the HOMO, the highest occupied molecular orbital. This refers to the LUMO, the lowest unoccupied molecular orbital. Now, bromide itself is a nucleophile, an electron donor. It will donate electrons into an unoccupied orbital. And the one it chooses to is the lowest energy unoccupied molecular orbital, the LUMO. And if we take a look at this, if we were to label the atoms 1, 2, and 3, 1, 2, and 3, there's only places where the electrons can go. It can only donate electrons to make a bond at atoms 1 or 2. Sorry, 1 or 3, not on 2, because 2 doesn't have a presence in this molecular orbital. So as a result, the bromide will add and form a bond with either 1 or 3 and not 2. And that's what we see. Now granted, we can get the same thing from resonance, but there will be a reaction later on where resonance doesn't help us predict products, or at least explain the reactivity. Now, notice I didn't draw in atom 4 into this molecular orbital diagram because we are dealing with the pi system, and carbon 4 is sp3 hybridized. There's not a p orbital on it. Can you have molecular orbitals of sigma systems? And the answer is, of course you can. To kind of give you an example of what another reaction would be, to use molecular orbitals to describe a reaction anyways. The reaction of bromine with an alkene, the first step generates the bromonium. So, molecular orbitals of ethylene, you have 2. You have the HOMO, and then you have the LUMO. The HOMO happens to be the pi bonding orbital. The LUMO happens to be the anti-bonding orbital. Now let's take a look at bromine. Bromine's orbital that we're going to be interested in is one of them is going to be an orbital that's high in energy, that has electrons in it. It may or may not be the HOMO, but it's basically lone pair on the bromine that is in a p orbital. And the other orbital of interest that's actually an empty orbital is this orbital right here. This is the anti-bonding orbital of the bromine bond, sigma bond. So here we have a filled orbital, and here we have an unfilled orbital. So let's have the filled orbital of the bromine interact with the unfilled orbital of the LUMO. And so here I'm going to draw in the LUMO. And I'm going to make sure that it has the right shading, because notice here we have dark interacting with dark, unshaded interacting with unshaded. The shading matches. And so what we're interacting with is the filled orbital of the bromine, basically the lone pair in that p orbital, interacting with the LUMO of that. And so thinking about and drawing curved arrows, we have the bromine's lone pair adding to the bibond. So that's the interaction taking place here. This forms a carbon-bromine bond, and simultaneously it breaks the carbon-carbon pi bond, because this because the LUMO is the anti-bonding orbital for the carbon-carbon pi bond. Now those electrons have to go somewhere, and so they have the LUMO, the HOMO. This is the filled orbital. It has 2 electrons in it. Notice the symmetry of this matches the symmetry of the unfilled orbital of the bromine-bromine antibonding orbital. So what happens is these electrons are used to make another carbon-bromine bond. That's this interaction right here. And since this happens to be the bromine-bromine antibonding orbital, that breaks the bromine-bromine bond, giving you this. And these interactions are occurring simultaneously. This is how two molecules are using its molecular orbitals to interact with each other. These interactions are always between a filled and an unfilled orbital. Okay. Back to the allylic system. Let's say we have allylic carbanion. This is sp2 hybridized, sp2 hybridized, sp2 hybridized. Again, we have our 3 p orbitals, and you end up getting pretty much them just like before. Now, unlike before, we have 4 pi electrons. Since we have 4 pi electrons, we add 2 to the bottom, and then we add 2 to the next one. So this is now the HOMO, the highest occupied molecular orbital, and this is now the LUMO, the lowest unoccupied molecular orbital. This molecule can react as a base take a proton off, or in this case a deuterium, like so. The other product that you get on this is this one right here. Base is an electron donor, so it's going to use the highest energy electrons it has, most likely. It's going to use the HOMO. And where there's sites of electron density are atoms 1 and 3. And so the deuterium ends up being added to atoms 1 and 3. Now, again, you can get the same results by using resonance structures. All resonance is molecular orbital theory that you can do on the back of a napkin. It's simplified molecular orbital theory. But sometimes you need to do a little bit more complex, and that's when we're going to be starting to talk about reactions such as the Diels-Alder reaction and how a cyclohexene is formed in just one step from these two starting materials. But that will be on Friday's lecture.